So we had completed about different fiber optic sensors and how the sensor classification is. Then we went for fiber optic instrumentation system where we had discussed about the attenuation loss measurement, followed by we went for certainly two different techniques, that is cutback method and then OTDR. And you know about optical domain time domain reflectometer. One, what is the purpose of OTDR is, right? And then we went for the scattering loss measurement, where the scattering power is going to be accounted for and how much it will be, and with respect to the fiber optic cabling. And then later we went to study about the fiber absorption measurement, where a thermocouple has been employed to measure such standards of absorption of temperature, which is directly related to what? Depending upon the amount of impurities that is going to be composed of. Clear? So if I have a fiber optic cable and if it is composed of impurities, it is surely it is going to give me what? An absorption of light energy. And if absorption of light energy takes place, you know well about it that it rises to a temperature. So the sudden increase in or rise in temperature with respect to my presence of absorption of light, it will be measured by means of what? A thermocouple. So we are going to have a total setup of a calorimeter. Clear? And this calorimeter will be surrounded by a index matching liquid. So the purpose of index matching liquid is, again, it is going to compensate for my cladding medium. You know about it, correct? And you have a dummy fiber and measurement fiber and so on, and you all must have understood how the working is. Okay, then what we went for is about the fiber dispersion measurements. So in fiber dispersion measurement, the system is going to have slightly a different phenomena, where you won't be having any kind of a cladding mode strippers or index matching liquids. Simply what we are trying to identify here is about the dispersion measurement. Clear? So what we need, a setup with sampling oscilloscope. And you know why a sampling oscilloscope is employed? A sampling oscilloscope has very high sampling frequency. Yes or no? Yes, it is. So the very high sampling frequency helps me with sampling my light signal. And you know, a laser light, a pulsed light will operate at very high frequency. So in order to capture such a high frequency signal in my APD photo detector, and if I want to sample that, I do look for what? A sampling oscilloscope. Clear? So then, after discussing about these dispersion measurements, we went for measuring the refractive index profile. In that, the first type is interferometric method. And in your syllabus, when we speak about the things that is going to be asked for, the interferometric method is alone going to be important. Okay, so I might have given you the complete working setup and how it works for measuring a refractive index in the last class. I do repeat it again in a short manner. Kindly do capture that. So for purposely measuring a refractive index in my test fiber, okay, if we go for an interferometric method of working principle, it was designed by Max Zender. Okay, these two persons designed the first interferometer which actively measured my refractive index profile. Clear? So the steps and procedures related to these refractive index measurement, you all know. I am not going to take on a whole fiber. Instead, I will go for a thin slab of fiber where I will take a slice of it. Clear? So we might have studied about Max Zender method in the previous classes in section of sensors. Clear? In that, we are going to consider it for measuring a physical parameter, but in terms of what? We are going to account for it as a sensor. Clear? Whereas now, as we discuss about, it is going to be completely related to refractive index measurement. So here, we are not going to take a complete whole fiber of a cable. Instead, we move for a thin slice. So the first thing will be the preparation of thin slab of fiber. So I will take a thin slice, I will cut it over, and what I will do it, I will polish it on the two sides. Clear? So I will make it optically flat, okay, into a form of a square plate. So this is your idea. So kindly listen through. The first preparation is going to be, I am going to take a thin slice, I am going to cut it over, and I'm going to polish it over the surfaces on the two sides, okay, so that it becomes optically flat. Okay, then the slab is going to be immersed in my index matching liquid. Clear? Now, as the second point as it goes to be, we are going into the interferometer principle again. So as we say, as the name interferometer, you all know, it is going to have a beam splitter, and this beam splitter is going to split my beam into an active and reference one. All right. So a beam splitter serves me a purpose for splitting the beam into what? An active one and reference one. So the active beam, we are going to have a reflection, and similarly the reference beam will also have a reflection. So for the purpose of reflection, we are going to have two mirrors, M1 and M2. So from the setup, it is viewed, correct? So you have a setup before you where you contain two mirrors, and these two mirrors correspondingly reflect my active and reference beam. Okay, so the logic is very simple. I'm going to create an interference of these beams, which will create or result me in a fringe pattern. Okay, so these fringes, if it has been measured, if at all my fiber slice is taken, and if this fiber slice is exposed, you all know that if the refractive index profile is subjected to my light rays of active beam, my active beam will have a slight difference in it. So as it interferes with that of a reference beam, the fringe pattern which is created, okay, the fringes which are created, it will be like as shown in the figure. Is that clear for everyone? Okay, so you might come to an understanding that my refractive index pattern inside my core will be more like a Gaussian curve. Okay, exactly at the center of the axis, it will be a dark node that represents the maximum value of the refractive index, and as it moves along, you can find a Gaussian pattern, a curvy pattern. Okay, and we are speaking about graded index fibers, and you all know that. Okay, so the measurement of refractive index profile is basically designed for the purpose of measuring what? Graded index fibers. And you know why? Because in a step index fiber, I could easily measure things. Clear? And if I measure that, the value is not going to change. It is going to be static all along. And if it gets varied, and it will also be in a step manner. Okay. So when we discuss about graded index fiber, okay, this graded index fiber will have a continuous change in refractive index. So we have a core cladding interface. The cladding refractive index value will remain more or less same. As we move into the core, with respect to the radius to the center of the axis, you might find the continuous change in the refractive index value. So for this purposes, we do go for what? Refractive index. Okay, capital D into X, and you know how it is being related. So these are all things that is being discussed so far. And when you look at the pattern of the graph that's obtained, you can also analyze that the maximum value occurs at the center of the axis. So as it moves along, you can find a curvy pattern. So it is quite understandable. Okay, so when we go for the power distribution, the power ratios on the core region and cladding region, and we might have seen these two formulas that has been shown to you. Clear? So this is all we have discussed so far, and what we are going to discuss afterwards now is about the end reflection method. And this end reflection method is not clear at all, but I will give you an explanation over it. Okay. So when we look at the fiber, the end of the fiber is going to be having a reflection. We are going to create a phenomena which is going to reflect my whole beam back again. Okay. So in the diagram, you can see a linearly polarized instant light beam is going to enter. Okay. A reflection isolator is present at the center, and it is going to focus through the lens, and the light energy is going to enter into the fiber. So the key point is creating an end reflection. So we are going to have the other end of the fiber completely reflective. We are going to make it that way. So after reflection, the same light energy is going to be focused into my reflection isolator. Clear? Yes. So the reflected light and the gathered light will be compared to create a refractive index. So this is how it is going to work. It is based upon the end reflection, but it is not quite important for you. What is important is refractive index measurement using an interferometric method. Clear? So this end reflection method I couldn't find in any of your books to be more clear and sound. Okay, so try to understand this. So maybe the limitation of these method can be taken. So the first point is the contamination of the fiber surface should not be allowed. Okay, if I find any contamination over the fiber surface, it will affect my end reflection measurement. Okay, and then in second, when we go for the fiber surface should be optically plane, because we are going to take a linearly polarized incident light beam. Okay, and the last point, during scanning, proper alignment of the fiber is necessary. So if at all, if there is any disorientation that is present, it will affect my measurement. So this is the idea behind the end reflection method. And maybe I could have given you about a basic thing, how the measurement of numerical aperture is. So we have different techniques, different related to numerical aperture measurement, and it is a very simple technique that is being shown to you. We have a Lambertian source, and you must ask me a question: what is meant by a Lambertian source? It is, so if I say Lambertian source, it is going to have a ray emission in a pattern such a way, at the center of the line you will have a maximum value. So as it moves away from the center of the line, okay, the center of the projection of the source, it is going to have cosine of the angle. So I might show you how it will be, okay, so that you might understand what it is. Clear? Okay, I will show you sample images where you can understand how a Lambertian source may work. Okay. Hope that it is visible for you. Now you can see a Lambertian source has been put over your presentation, where you can see an optical source containing different beam projections, and you can see I is going to be the luminous intensity. Now what you need to understand here is this beam will be maximum at the center. So as it moves along the circle of projection, that is over here, it moves away with an angle of cos theta. So when you take exactly at the position of the source 90-degree perpendicular, the I value will be 0. So this is how the understanding should be. So this is how a Lambertian source works. So hope I made this clear for you. Am I right? Any doubts you have? Do you understand about Lambertian source? Yes? No? Answers please. No answers. So is my screen visible for everyone? None. Put it in the chat box, please. Okay. Is my voice loud and clear? Are you people able to hear me? Yes? Okay. So hope everyone listens my class. So what I am trying to say is we are going to incorporate a Lambertian source. Okay. So the Lambertian source has a beam of projection with a cosine of angle, where the center axis projection will have maximum intensity. So as it moves along the curvy line, it is going to have a cos theta terms to be multiplied over. Okay. So I'm going to have such a source, and if it is being focused into my fiber optic cable through a lens, what happens? So then that is what we are going to see. So after it gets exposed, we are going to have a screen before me, and this screen is going to be separated by a distance d. Okay, so we are looking for a distance at which the maximum light intensity is can be accounted for. Okay, so it could ask me at what distance d I should place the screen. So the answer will be I need to gather an highly visible light which has a position of high intensity to be visible. Clear. So that way I'm going to keep a distance. So after projection, this light is going to be focused upon my screen where it is going to create and what could I say is it is going to project with uh, a visible light. Clear. So this pattern what I obtained or a diameter what I obtained, if I measure the area in terms of a meter, it is going to give me the what numerical aperture that is going to be associated with the fiber optic cable. So this is how the understanding is, and that is how we are going to measure numerical aperture. Clear. So this is how the measurements are being done. And coming to near field scanning techniques, again, this technique is also for what we say measure for refractive index. Okay, so here also you can see a Gaussian pattern that is going to be created with respect to XY recorders, and we are going to make use of what a Lambertian source. The purpose of having a Lambertian source is if I create a deflection angle, I could create a deflection angle, and if it is so, it will be in terms of cosine of theta. Okay, so I could create different deflection of angles from the same source. Okay, and it is going to be focused upon my fiber. After successive passing through, the lens 1 and lens 2 is going to do the same purpose, focusing in and focusing out, but my lens 3 is going to diffract my beam into the chopper. Okay, so the diffraction beam after obtained from the lens 3, that is going to be fed into my chopper, rather into that of the pre-amplifier circuit accompanied by a pin diode. Clear. So we have a transverse scan pin diode that is going to accompany my chopper. Okay, and it is going to measure my the refractive index profile again. Okay, and you know what this refractive index profile is. We are going to have a change in light radiations, the angle of light incidence after it is getting passed through my fiber cable. Okay, so what we will have is after obtaining this, I will give it to our XY recorder to plot the curve, which is again a Gaussian pattern. But again, what I am trying to say is this technique is not also quite clear. Okay, so we need to understand the interferometric principle to be more elaborate, and you need an understanding about end reflection and near field scanning technique. Okay, and we had a thing about the measurement of numerical aperture of the fiber now. Then to speak about the modulators, which is already discussed, about the principles behind. Am I right? So when we say about optic modulators, we are going to have a change in light intensity that happens because of the change in refractive index. Okay, with respect to the parameter that is going to be varied as an input. Clear. So when the types of external modulators are discussed, we had three different types. One is electro-optic modulators based upon Kerr effect. And second one is magneto-optic modulators based upon Faraday effect. And finally, the third one is about the acousto-optic modulators, which depends upon the photoelastic effect. Clear? So you know the working principle that the Kerr effect is nothing but the change in refractive index will be proportional to the square of the applied voltage. So certain materials do exhibit this change in refractive index because of the applied voltage, applied electrical energy. Clear. Similarly, the same thing, if it is being carried forward with the applied magnetic field, we will have a successful change in rotation of the plane of polarization. Okay, and it is again indirectly related to what change in refractive index. So that is what we have seen so far. So in electro-optic modulators, the applied voltage will change my what refractive index directly, whereas in a magneto-optic modulator, we do find the change in plane of polarization because of the applied magnetic field, and this change in plane of polarization is going to related one way with what my refractive index change. Okay, and the disadvantages, if I say the magneto-optic modulator suffers, it requires a high value of applied magnetic field to have a quite small change in my angle of rotation. Clear? And similarly, it can also exhibited by the angle of rotation depends upon the wavelength too. Okay, so if at all my wavelength changes, there might be a possibility of angle of rotation also. So this is your disadvantage that we speak for in magneto-optic modulators. But why to study these optic modulators? What is the purpose then? So we employ fiber optic sensors in different areas. Okay, and that too in especially in measuring current and voltage. When we for employing these fiber optic sensors, we need a change that's going to happen because of an electrical energy or magnetic field. Okay, so that is the understanding part. Here it is. So we are going for optic modulators simply for the purpose that we are ought to measure current and voltage. So if I happen to create a change to my optic fiber cable with respect to electric field, that will pay me a path to measure what voltage. And similarly, if I have a change of a plane of polarization with respect to my magnetic field, that will help me a lot in measuring what a current. Okay, and these are all accurate measurements. So we are speaking about fiber optic sensors. Okay, so everything will be more accurate. Clear? So and the last one, the acousto-optic modulators. It is nothing but it depends upon the photoelastic effect. So the acoustic waves is going to create a change in my refractive index. Okay, the change in refractive index of the medium will be because of mechanical strain. That is clear. But this strain is produced by what? Acoustic sound waves. So these acoustic waves, if it affects my medium, it is going to create a mechanical strain followed by change in refractive index. Clear? Okay. So is my voice loud and clear? Is my presentation visible? Yes or no? So kindly do put up in the chat box so that I could understand whether it is. Yeah, thank you. Okay, now we are going into the techniques where the measurement of length is going to be done by using an interferometric method. Now what you see here is a diagram which depends upon the same principle of interferometry. Okay, so you know the basic idea here it is. So you will find a beam splitter. All right. So whenever we speak about interferometric method, you will find a beam splitter there. Correct? So this beam splitter is the key phenomena here, and it is going to perform two actions. One is beam splitting, other one is joining. Okay, so the same beam splitter is going to act as a joiner and a beam splitter. So our laser energy is focused. Now what happens as it leaves the beam splitter? It is going to be split up into two. One is active and another is reference beam. The reference beam will be focused upon a fixed mirror where it will be redirected to the photodetector, whereas an active beam which is focused here. Okay, this is reference beam. This is active beam. So this active beam, if it is being focused to the cube corner reflector, which is movable. Okay, so kindly do listen. We have two mirrors. Okay, now what I'm going to do is I'm going to call a fixed one as a mirror, whereas the movable one as a cube corner reflector or a reflector one, a movable reflector. Now what happens? This movable reflector or cube corner reflector will also have a mirror to be present here. Okay, so now as it moves along, this cube corner reflector, as it moves along, what happens? There is a change in my interference that is created afterwards as it travels back and forth. Okay, so again the fringe pattern will be created. Now the fringe pattern is not about the refractive index, is not about any other parameters. It is going to be about what? The fringe displacement is going to be about the distance that is going to be covered. So the laser energy which is focused and which is split into reference and active, as it meets again back at the beam joiner, you will found to create or you are found to see interference pattern to be created, and that will correspond to my photodetector. So if I map my interference displacement value to that of the photodetector, I could easily measure what? The distance covered. Clear? and this is how your measurement of length is going to take place. So is that clear for everyone? Any doubts you have? That is more simple. It is a previous technique that we have discussed so far. The same interferometry, the same kind of principle, but for measuring different things. Yes, PPT is not visible. Okay. Is it visible now? Yes. Lambertian screen is present. Okay. Maybe sorry. I will represent it now. See that if it is visible. If not, kindly do tell me. I will represent it again. Look for the screen. Is it visible? Okay. Now I might have marked something in red color. So that is how the working phenomena is. Clear? Yes. So we have a beam splitter cum joiner to be present. Same interferometry principle. The laser is going to be focused, and we are going to have a fixed mirror and a movable cube corner reflector. And if this cube corner reflector, or we could have like this, a movable mirror to be present and a fixed cube corner reflector. Okay, both ways it can be. The same principle can have a movable mirror here and a fixed cube corner reflector, or we can have a fixed mirror and a movable cube corner reflector. No problem it is. So both ways it is going to create a change in fringe pattern, and this fringe pattern, if it has been analyzed, we could identify what the measurement of length or distance. Clear? Yes? Any doubts you have? Yes, no? Answers please. Clear or not? Answers. So we may proceed with other applications. Okay. So now as we speak about these techniques, where do we find applications for these? So these are all used in aircraft components machining. Okay. So these are all very much accurate. These interferometric based distance or length measurement, they are going to use it in positioning of aircraft components. Clear? So this is how it is going to be. Yes. Now coming to Moir fringes, we will discuss this in the last, because certainly it may bore you. Okay. So we are going for measurements using fiber optic sensor, where the first measurement is going to be about pressure. Now look at the diagram and tell me either it is an intrinsic one or extrinsic one. I do need answers. Either it is an intrinsic one or extrinsic one. Is my screen visible for everyone? Yes, I think. Okay. Okay, very good. It is an extrinsic one. You know why? Because the fiber is going to simply transmit and receive my signal, and it is not going to act as a sensor. Now this measurement of pressure, you can see a diaphragm to be present. Clear? This diaphragm is going to reflect my light intensity, which is focused upon. If my diaphragm is going to get increase in pressure, the diaphragm will converge more or it will diverge more. Okay, and this is how the reflective concept is, depending upon the fiber optic cabling with respect to pressure sensor. So what we have here is, we have a diaphragm which bends backward and frontally because of the increase in pressure. Okay, so if I find increase in pressure, we happen to have my diaphragm to converge more. Okay, and if this happens, my light intensity reflection will vary. Clear? And if my light intensity variation changes, if I map it to that of the pressure difference, I could analyze how much pressure is being present inside my corresponding medium. Clear? So we have a response curve pattern for pressure sensor. So it is visible, I think. So the y-axis is going to be output in terms of voltage, whereas the x-axis is going to be in terms of pressure PSI. So this output in terms of voltage is going to be by a photodetector circuit. So photodetector circuit, you know the conversion of energy how it is from light energy into that of one electric one. So if my intensity variations happens through, my light energy is going to get decreased such a way the electric energy that is going to be coupled over will also get a difference. So similarly, based upon that, this is how the pattern or the response curve for a pressure sensor based upon the fiber optic cable will work. Okay. Yes. So you can see that the increase of pressure, the intensity of the reflected light is decreased. Hence, output voltage will also decrease. Okay. So hope I made this clear for you. Coming to the next measurement of temperature, this is very much familiar, and you also know that it is also an extrinsic one. We do have a bimetallic strip or element to be present. The increase in temperature will cause me again a bending of this bimetallic strip. So this happens to create a change in reflection angle. The change in reflection angle accompanied by lowering of my intensity. So this happened to create a change in output voltage. So if I map it again with respect to voltage V and temperature increase, you again see the same kind of response curve, which is similar to that of a pressure sensor. Okay. Yes. Now, about phase modulator sensor. This is also already discussed. Okay. So we have a 3 dB fiber coupler and at both sides. So what we are going to do is we are going to split the beam. We are going to send it through a reference fiber where no temperature is going to affect. Here a temperature change will affect, and if this happens to create a change in my light intensity, or you will happen to have a change in refractive index pattern, and that refractive index pattern change will accompany with what? Change in the light traveling parameter. It may change or it may affect my phase of my light signal, or it may affect my intensity of my light signal, or it may affect my dispersion of my light signal. So the parameter or principle what I look for is to have a change in my any one of these parameters. Okay. So successfully on finding out it in my display, I could identify the temperature that is being present in my sensing fiber. Okay. So the same arrangement, it depends upon what? Again, Mach center. If I say Mach center, you can see two beams have been split, one active and one reference, and it is going to be coupled again. Okay. So you can see there is this name again and again in all the topics that we have discussed so far. Okay. It all reminds me the same kind of principle. Okay. Yes. Now coming to measurement of voltage. Okay. So this is going to be the equation which is going to govern the Kerr effect, where the refractive index change, okay, which is related to that of the electric field. Now, if my Kerr effect is accounted for, if I take an electro-optic modulator and if I use it for measuring voltage, my change in electric energy or voltage applied or potential difference will try to change my light parameter. Okay, because the refractive index changes. Since my refractive index changes, the traveling path of my light changes. That may affect my intensity. That may affect my dispersion. So that is how we are going to measure my voltage. Okay, even the phase differences will also be accounted for. Clear? Similarly, if we go for measurement of current in terms of magnetic field, now look at the setup. We are going to have a single mode fiber here, and in this single mode fiber, it is going to carry me a polarized light. So we can see a helium neon laser as a source that is going to be fed to a polarizer. After the polarizer, the light that is going to enter in my fiber cable is going to have a single path of travel, which is also a linearly polarized. And if that light enters into over my current carrying conductor, what happens? This current carrying conductor has the capability of creating a magnetic flux pattern. So this magnetic flux distribution and flux intensity changes variations will also affect my light energy, or that is polarized, which happens to create a change in polarization angle. And if I analyze that change in polarization angle of my resultant light radiation through a Wallaston prism, and this Wallaston prism is going to create two beams, I1 and I2. Okay. And if it is being combined over, and if I analyze that particular output, I could analyze my change of polarization clearly. So this change of polarization is going to be a direct effect of magnetic field, and this magnetic field will be affected with my amount of flow of current. So indirectly I measure what? Current here. So that is the idea behind the measurement of current using fiber optic sensor. Okay. So what do they give us? An expression carrying k times theta r. Okay. Theta r is the polarization state rotation, which is given by two orthogonal components of I1 and I2. I1 and I2 represents the intensity of light that is happening after the Wallaston prism. If these two components are analyzed, I could understand what the polarization that is taking place. And this is how your measurement of current is going to be done. Clear? Now coming to strain. You know, a simple strain mechanism that we have discussed depending upon the microbending losses. Okay. Now the setup, if you look at, it is going to carry a light source simply present here, a beam splitter. So a reference beam enters here, which is fed to a comparator. The active beam which enters into this mechanism is exposed to difference in strain or force applied, which in turn creates a microbending. You know about microbending. We are going to have an arrangement which is present before. That is discussed already. Okay. I will show you. You might remember things. So here we have discussed about microbending sensor, right? A deformer is present. A similar kind of deformer will be present there in terms of strain measurement. Okay. And that is going to be present in between this system where force is going to be employed, and particular force acting upon it will create a microbending over my fiber optic cable, which in turn affects my intensity of my transmitted light. And if it is being compared with the intensity of the reference beam with that of an active beam, I could find what? The change in light intensity. So the difference in light intensity is going to impact with my force. So this is how it is going to be measured. So the force or strain can be measured by this principle. Okay, and one more topic is there where you need to know about pocket cells. Okay, then I will show you about what is a pocket cell. See that my slide is clear for you. I'm going to put up a window. See that it is visible. Yes, hope it is visible for everyone. So Pockels effect. What is Pockels effect? So what you need to understand is Pockels effect produces birefringence. So kindly do listen, look. So the birefringence that is created, I will highlight. Okay, so I think I have highlighted. Is it visible for everyone? Yes, no? Answers please. Visible? Yes, okay. So Pockels effect is nothing but a kind of electro-optic effect where if I apply an electric field, it produces birefringence. So what is birefringence? That will also I show you. You have image for birefringence. So is it visible for everyone? I could show you a diagram where a light get splits into two patterns. Okay, that you can see here. Yes, two components resulting from birefringence னு போட்டிருப்பாங்க. நல்லா பாருங்க. ஒரு polarized plane light போகும்போது அந்த light, if it is being subjected to an electric field, it will result in two components that we call it as what? Birefringence. Okay, which get differently polarized. Two light beams of get differently polarized, and you can also see here. This diagram will also be very clear for you. I am going to have an incident light, and that light is going to be split up into two polarized conditions. See how it is being polarized before and after. Okay, both has different kinds of polarization. That is how it is going to split, and we do call it as what? Birefringence. So if I happen to have such a kind of condition when I apply an electric field, we call that as what? Birefringence. Okay, if I happen to have a birefringence to happen, we call that as a principle of pocket cells. So that is how the understanding should be. So hope I made this clear for you. Yes, any doubts you have? Clear? Yes, no, answers please. Okay, now you will get back to the presentation again. See that it is visible. We are going for measurement of liquid level now. So we have two kind of interactions and basic principles behind measurement of liquid level. So one is going to be upon total internal reflection. Another is going to be upon the refractive index change. So you have two sets of diagram. One is going to be working upon the total internal reflection that is going to take place. Another is going to be upon the refractive index change. So this diagram, first diagram, you are going to have a microprism. That is the working logic, where this microprism is going to give me what, which is present here, is going to support me with total internal reflection. So if there is no liquid, my light source, which is focused through my fiber optic cable, will successfully have total internal reflection, and my receiving cable will receive the light intensity to the detector. Okay, now the connection is complete. The light energy passes through, gets totally internally reflected, reaches my detector. Whereas here, if my liquid level increases, as it affects my refractive index over the surrounding area of the microprism, this microprism's overall refractive index pattern changes. What happens? Here, no total internal reflection takes place. So there is no signal from the detector. Clear? So this is how measuring of liquid level using total internal reflection works. Okay, coming to the second part. Here, we are going to again make use of fiber optic sensor, where the refractive index is going to change. There is no cladding at all at the area where the fiber is going to be immersed. Now, as the liquid level changes over and down, what happens? The refractive index value surrounding the core will change. The whole optical fiber cable will be let inside my liquid. Okay, now the refractive index change will happen to create reflections and the light intensity variations. So what I will do is I will analyze the intensity of the light that is being sent and reflected. So this will give me what? The corresponding change in my liquid level. Okay, so the advantage of the previous and the method that is discussed now. So you can see a microprism has been employed where total internal reflection takes place. So if there is an increase in liquid level, I don't find any internal reflection. If there is no increase in level, I will find total internal reflection. So you can have the liquid level to be measured simply with either in or out of total internal reflection. Now, the second type corresponds to change in light intensity. Okay, so here the understanding is we cannot employ this particular technique for multi-liquid levels. that is based upon total internal reflection. But this technique can be employed for multi-liquid levels. So depending upon the increase in levels, I could find change in interactions with my surrounding liquid to the refractive index change, where the intensity of the light that is being coupled after will have continuous changes. Okay, so we can find different levels of liquid from a single setup by using what? A refractive index change. So these are the different types of sensors, and we are going to complete unit number 2. Okay, from the next class onwards, next session onwards, we will discuss about what? Unit number 3. We will have a brief introduction about unit number 3, and we will go in detail. So any doubts you have in unit number 2? If at all, if you have any doubts, you can put it in the chat box, or I could answer you now. You can unmute yourself. Any doubts you have? Anyone? Clear? Yes? No? So we are trying to wind up the session. I need to take the attendance. So kindly do answer me. Okay. So I do acknowledge you, students. So please do listen to the classes. So we will have questions in the next class about the session that has happened today. Okay. Thank you. I will take up the attendance so you can leave.